start this thing. So we have, today we're going to be talking about what's called the normal random variable. It has several names. So one of them is the normal random variable. Others sometimes call it the Gaussian distribution. And there's several reasons as to why they call it normal and why they call it Gaussian. Well, one reason why they call it Gaussian is due to the mathematician Carl Friedrich Gauss, considered to be one of the greatest mathematicians ever. He was the one that saw a very good application of this random variable. And the reason why it's called normal is because, as we will see later, many random variables or data sets, distributions, they tend to have a certain similarity as we have large and larger number of data points, and they tend to have a distribution as those data points get larger and larger. It tends to have a distribution similar to the normal. So I think many of you may have seen this already. But the first thing that's very striking about the distribution here that just fell out of whack is the symmetry behind it. It's very nice. It's a very nice symmetry. They call this a bell-shaped curve. Bell-shaped curve. So when you hear the word bell-shaped curve, immediately think the Gaussian distribution, immediately think normal random variable. And the way this is distributed, so this is the probability density function. This is the graph of the probability density function of the normal random variable. And of course, it's symmetric. It's symmetric about the mean. Now the mean is smack dab in the middle. So it hovers symmetrically about the mean. And the way this is spread out are what are called the standard deviations. So this is where standard deviation becomes very important. So as you move to the right, all these tick marks here are equally spaced by what's called the standard deviation. So to go to the next tick mark, you're just adding the mean by the standard deviation. So again, this is the mean, the average. And this will be the standard deviation. And as we continue on our way to the right, we're just adding another additional standard deviation. So this would be mu plus 2 standard deviation. This is mu plus 3 standard deviations, and so on, right? And then again, this goes to infinity. So this is a continuous random variable that is defined from negative infinity to infinity. So theoretically, this little graph here gets really close to 0. So you can think of the x-axis as being an asymptote as you move to the right indefinitely, and the same thing goes for moving to the left indefinitely. So let me just put this as saying that I'm going to positive infinity. This is to negative infinity. But the bulk of what the area, the bulk of the area underneath this curve occurs within these 3 standard deviations. So then let's also talk about going to the left. This is mu minus standard deviation. This is mu minus 2 standard deviations. And this is mu minus 3 standard deviations. It's a very nice curve. Very nice. So the idea now, guys, is the area underneath this curve will give us the probabilities that my random variable, which is normally distributed or a normal random variable, is within a certain range. So if I am within this, if I am within this range of values for x, so here, all these values here are indicative of being what's called within 1 standard deviation from the mean. So then, so let me just say this is let x be a normal random variable. So when I say x is between, the values of x is within mu plus theta plus rho, which is sigma, pardon me, mu plus sigma, and mu minus sigma. This indicates that the values of x fall within 1 standard deviation from the mean. And then if we have 2, if x is between mu plus 2 sigma and mu minus 2 sigma, so this includes all of this. This area here would represent the probability that my random variable attains those values between mu minus 2 sigma and mu minus 2 plus 2 sigma. But this indicates that the values of x fall within 2 standard deviations from the mean. So we care a lot. We care a lot about being 1 standard deviation, 2 standard deviations from the mean, and so on. And we could also talk about being 3 standard deviations from the mean. Yeah, so let's do that. So this is mu minus 3 sigma, x is between mu plus 3 sigma. And this is values of x fall within 3 standard deviations from the mean. Now there's what's called a 68, 95, 99.7 rule. There's a rule. And what does that rule indicate? It indicates that approximately the probability that my values of the random variable that I have falls within 1 standard deviation of the mean is approximately 0.68. And we'll see this. So this percentage wise, 0.68 percentage wise is 68%. So what am I saying by this? What does this mean? This means that the probability that my random variable will attain a value that's within one standard deviation from the mean happens 68% of the time, approximately. There's a bit more precise number, but it's approximately 68%. And the same thing goes for mu minus 2 sigma x mu plus 2 sigma. So what is this saying? It's saying that the probability that my random variable attains a value within 2 standard deviations from the mean. So this region here will tell me the area will tell me the probability that my random variable will attain something within 2 standard deviations from the mean, which is anything between this interval. And that happens 95% of the time, 0.95, which is 95%. So 95% of the time, this random variable will have a value that is within 2 standard deviations from the mean. And then last but not least, we have this. So when you're within 3 standard deviations from the mean, this nearly happens the area underneath this region will tell me what's the probability that my random variable will be something within 3 standard deviations from the mean. And that the probability is 0.997. So approximately. So this is 99.7% of the time your values for your normally distributed random variable will attain a value within 3 standard deviations of the mean 99.7% of the time. So they call this the 68, write this as the 68, 95, 99.7% rule. So this is a rule that every random variable, no matter what it is, no matter what mean or standard deviation it may have. So the parameters of a normally distributed random variable of a normal random variable. We have the mean and we have the standard deviation. So these are really the only things we need to determine everything we could know about the normal random variable. We need to know the mean and we need to know the standard deviation. So let me just ask, is anybody familiar with this? Have people seen this before? The Gaussian in physics? Really? Physics? Where exactly in physics, Alexandra? IQ distribution? Okay. I've never seen Gaussian in physics. That's interesting. Quantum physics. Okay. That really, I've never taken quantum physics. I've heard about it. I didn't know it popped up in quantum physics. That's pretty cool. Yeah, this curve is amazing actually. Oh, the probability. Yeah. So see, that's amazing that this distribution um, this Gaussian normal distribution is so prevalent in various different fields. So you can see this in quantum physics, the probability of a particle being in a particular location. That's pretty interesting. It's used for test scores, right? How the distribution of test scores on standardized tests. That's what they normally go by. It's uh, there's like the distribution of the heights of people in the United States, for example. Like there's a certain average, right? And then everything kind of tapers off very nicely. And there's other various, numerous applications of this one distribution. So this is one of those special ones. It really is. Um, okay, well, I'm glad some of you have. It's kind of expected expected that many have seen this uh, distribution before because it's so useful and it appears so much in our lives. Okay, so of course we're not just going to stick to this, right? This is a pretty introductory um, explanation of what a normal random variable is. And what we also very much care about is the probability density function. So what is the probability density function? So this is when it gets a little more mathy. And this is probably the more complex probability density function that we have seen thus far, because it has uh, very interesting constants that appear. So the probability density function has this form. This is 1 over the square root of 2 pi. Already, it's like, wow, where did that square root of 2 pi come from? So it's 1 over the square root of 2 pi multiplied by the standard deviation sigma times e. So another transcendental constant. So we have two transcendental constants. We have pi and we have e. So we have Euler's number and the pi embedded in this probability density function minus, and it's e is being raised to x minus mu squared all over 2 sigma squared. And all of this, and x is, like we was said earlier, the values of the random variable is continuous. So it's defined on the interval negative infinity to infinity, which is it's defined on all real numbers. And so this is my probability density function. So when you're to graph this, when you graph this on the XY plane, you get the bell curve, the very nice bell curve. Okay, this is the PDF. So has everybody seen this before, the probability density function? No, okay. Yeah. Some of you may have, but yeah, this is very crazy looking, but it has a very beautiful symmetric uh, graph. Okay, so then the question now becomes, is this a legitimate probability density function? Is it legitimate? So then what would make this legitimate? So let's show that the above PDF is an appropriate one. So this would mean, so i.e. the integral from negative infinity to infinity of f of x dx has to equal 1. So this here when you set this integral up, this should give me 1. Now this looks pretty complicated, doesn't it, to show? Well, first of all, this here is a constant, so we can move the constant outside of the integral. So this here is 1 over the square root of 2 pi times sigma, negative infinity to infinity, of e to the negative x minus mu squared all over 2 sigma squared. Okay. All right, so this is dx, right? So really, I care only right now about this. So I want to show this is true. So what we're going to do is we're going to look at just this integral here. So we have negative infinity to infinity of e to the negative, this is x minus mu squared all over 2 sigma squared dx. So a lot of this stuff will require some algebraic manipulation and some use of a little bit higher techniques in integration. So what we're going to do is we're going to say let, let's see. Yeah, let y be x minus mu over sigma for now, okay? So I'm gonna rewrite this as, so making that change of variables, I get the integral from negative infinity to infinity of e to the negative y squared over 2. And then if you look at dy, what is dy? Dy is dy is 1 over sigma dx, which would mean that dx is equal to sigma times dy, right? So then this sigma appears up here, and I have dy. Does everybody see that? So dx, this is a change of variables. So dx becomes sigma dy. So I have a dy and a sigma outside because it's a constant. And then I have this little simplified integral. So now the question becomes, what is this? This is the bulk, this is the crux of the problem. So what is the missing value here of this integral? So negative infinity to infinity of e to the negative y squared over 2. What is this equal to? So this is one of those things. It's a little trick here. I'm gonna call this I. Let this equal to I. So then because these, remember, if you remember in Cal 2, these were dummy variables, quote unquote, they're dummy variables. So I can rewrite this also as negative infinity to infinity of e to the negative. I can replace y with any other variable. So I can call this x squared over 2 dx. Again, this are just called dummy variables within the integral. So then why do I write this in 2 different ways? Because now when I multiply it, I get I squared. and I get the integral from negative infinity to infinity of e to the negative x squared over 2 dx, and I multiply this by the integral of negative infinity to infinity of e to the negative y squared over 2 dy. So now you may say, hey, you know what? You just made this more complicated. Well, what we could do here is we can create a set of double integrals. So I can write this as negative infinity to infinity, negative infinity to infinity of e to the negative x squared over 2 times e to the negative y squared over 2 dx dy. But then why is this good? Well, this is good now because by the laws of exponents, I can combine these two things and I get e to the negative, and this becomes x squared. So parentheses x squared. Is it x squared? Yeah, it becomes x squared plus y squared over 2 dx dy. And so this is when we use another change of variables. We have another change of variables. And you guys have to remember that x squared plus y squared, we can rewrite this as r squared. So we're going to say r squared is equal to x squared plus y squared. And then, so that's when, this is when x equals r cosine theta, y equals r sine theta, right? And then we have this thing called the Jacobian. So dx dy, this becomes r times, yeah, it was d theta dr. So when we put this all together, we get the following. So the change of variables, right? Remember, this becomes dr now, and this becomes d theta. So r goes from 0 to, it goes from negative 0 to infinity, pardon me, so this should be switched. This is dr d theta, right? So then the interval for theta is 0 to infinity, and this will be 0 to 2 pi. Pardon me, 0 to 2 pi is for theta, and r goes from 0 to infinity. Now, why is this the case? Theta goes from 0 to 2 pi because we're including everything around, right, the region from 0 to 2 pi, and r goes from 0 to infinity because x and y go from negative infinity to infinity, but because it's squared, it's always going to be a positive number. So r will always be something from 0 to infinity because it's a positive quantity. And theta ranges from theta, this x here, it ranges from 0 to 2 pi. And then I get e to the negative r squared over 2. And what saves all of this is this extra little variable that I have due to the change of variables, this little r here. And because of this r, I can now solve this. So what is the inner variable, inner integral here? 2 pi r times e to the negative r squared over 2 d theta. What is, oh, I just saw this. So Alexander, you've never seen a double integral. Yeah, it's usually in, I guess, in multivariable. But the double integral is, for at least for this example, is really just an integral within an integral. Yeah. Again, this is just to show. All we're doing is we want to show that uh, the PDF that we originally were given, that's defined, we just want to show that this, when you put from negative infinity to infinity, it equals 1. That's all we're going to show. So at this point here, right, at this point here, we have this integral. And then after we're done with this integral, we're going to apply the other integral. So this integral here, how do we deal with this? Well, we can do u substitution, right? We can say u is what? U is r squared over 2. And then what is du going to be? Du is going to be 2r over 2, which is just r, right? So this becomes e to the negative u. And of course, oh, pardon me, this should be, oh, so before we do that, we have to recognize something. You see this? This is a function in terms of r, but our integral is for theta, is with respect to theta. So this entire thing is treated as a constant. So you can take this constant outside of this integral, and so I'm just going to write it like this. So this is 0 to infinity of r times e to the negative r squared over 2, right? This thing here is just from 0 to 2 pi of d theta times dr. So do you guys see what I just did here? I removed this and put this outside of this inner integral. And what this here will be the constant function 1, right? And the interval will be from 0 to 2 pi. So when you do that integral, what you're left with here, what pops out here is a 2 pi. So this 2 pi pops out. So let me erase this here. So this is not here. So we get 2 pi. And then here, this is 0 to infinity of r e to the negative r squared over 2 dr. So this is where we care about. This is the last thing we have to worry about now. And then again, this is where you do the u sub. So this is u equals, let me just write this as r squared over 2. So that means that du is r dr. And so the bounds here remain the same, 0 to infinity. And I'm left with e to the negative u du, right? Because we have r dr pop out, and this is equal to du. So now what is this integral here? Well, this will be negative e negative u from infinity to 0. This is an improper integral. So this will equal what? 2 pi e to the negative. So if I'm taking the limit as u goes to infinity of negative e to the negative u. So if this is going to infinity, I'm going in the negative infinite. So if you look at e to the negative u, it looks something like this, right? So as I go to infinity, this whole thing becomes closer and closer to zero. I get closer and closer to zero. So this becomes zero. And then I do minus e minus negative e to the 0th power. But negative times the negative is a positive, e to the 0 power is 1. So this entire limit, integral here is just 1. So what am I left with? I'm left with 2 pi. So all I've done is I've shown, what have I shown? Shown that I've shown that I squared is equal to, what is I squared equal to? I squared is equal to 2 pi. And remember what I was, right? So I, when you take the square root of everything, is the square root of 2 pi. But what was I again? I was, so the integral from negative infinity to infinity of e to the negative y squared over 2 dy, this equals the square root of 2 pi. Now go all the way back to this moment in time where we had this, right? And remember, this entire expression equaled this. And what am I saying now? I'm saying that this is equal to sigma times, sigma times square root of 2 pi. But why is this good? Because we're trying to show that the PDF that I'm given indeed equals 1. Well, I've just shown that this integral here is equal to sigma times the square root of 2 pi. And this here was being multiplied by 1 over square root of 2 pi times sigma. So these two constants will cancel out and I get 1. Okay, so let me just play that forward. So originally, right? Originally, what do we have? We had the integral of 1 over the square root of 2 pi sigma, negative infinity to infinity, of e to the negative y squared over 2 dy. And remember, this was already from a, so let me rewrite this. As this is x minus sigma minus mu squared over 2 sigma squared dx. And this, I rewrote this using change of variables as negative infinity of e to the negative y squared dy. And this little sigma popped out. And then I just showed right now that this is 1 over the square root of 2 pi sigma times the square root of 2 pi. So then you have things that cancel out. And this indeed equals 1. So all of this was just to show algebraically that the PDF indeed is a PDF, because the integral of that PDF from negative infinity to infinity equals 1. Okay, I'm just letting you know this is probably the longest derivation we'll probably do, so don't get too bogged down with the details. I know some of you may have not seen double integrals, but which is a bulk of this derivation here. This is a simpler kind of double integrals because you're dealing with two functions that have different variables. So really the hard part here was the change of variables for a double integral. And that is a bit more probably outside the scope of this course. So don't get bogged down too much about these little technical details. Just understand that indeed it is. Indeed, this whole little integral that we have here, which looks kind of crazy, actually has a very nice property that the integral is equal to 1, which constitutes this as a PDF. Okay, so now with that, we can show what the expected value is. So what's the expected value? We care about the expected value, don't we? So I'm going to show you a bit of a slick way of finding the expected value of a uniform random variable. So what is the expected value formula again in the continuous sense? Well, it's the integral from -infinity to infinity of x times the probability density function f of x dx. That's the definition, right? By definition. And of course, we're dealing with the normal random variable. So this will be equal to the integral from -infinity to infinity of x multiplied by 1 over the square root of 2 pi sigma times e to the negative x minus sigma minus mu squared all over 2 sigma squared dx. We can take the constant outside. There's not going to be any double integrals, so do not worry about double integrals. So this is going to be 1 over the square root of 2 pi sigma times the integral from -infinity to infinity of x e to the negative x minus mu squared all over 2 mu squared dx. Okay. So here's the little trick. Here's the little trick. And then you're like, wait, you can do that? And I would say, yes. Yes, you can. So the trick is here. This is a little trick. And this happens a lot in mathematics where there's like just an algebraic manipulation of things. And then you may, at first, when you see this, you're like, wait, we can do this? So I'm going to replace this x, okay? I'm going to say let x equal x minus mu plus mu. And then you're like, what? Why does this work? So look at this. This is 1 over the square root of 2 pi sigma. So do you guys see how this is the same? X equals x minus mu plus mu because the negative mu plus the positive mu just cancels out. So theoretically, technically, I didn't really do anything. I just rewrote x by adding a 0. X plus 0 is just x. But I'm doing this in a certain way because it works. It just works. So whoever came up with this is very, very clever. So this will be, I'm gonna write this as x, and then this would be minus mu, right? And then plus mu. But I'm gonna treat this together as one little thing. And this entire thing is being multiplied by what? E to the negative x minus mu squared over 2 mu squared dx, right? So everybody with me so far, all I've done is I've done this little addition and subtraction of mu. That's all I've done. Now when I distribute this, I can distribute and create two separate integrals, okay? Not double integrals, but I'm just creating two separate integrals. So try to follow along here, and we'll get out of this derivation world a bit, hopefully sooner than later. So this will be e to the negative x minus mu squared over 2 sigma squared dx. And then I'm going to have the same thing plus 1 over the square root of 2 pi sigma integral from -infinity to infinity of mu e to the negative x minus mu squared over 2 sigma squared dx. Okay. Everybody with me? All I did was I distributed this to this parentheses, And so I have this integral here, and then I separately, because of the addition, I incorporated this with the mu here, and constant outside tagged along. So I distributed and split. That's what I just did. Okay, I distributed and I split. Make sense? Now things clear up really quickly after this. Again, there's a lot of these change of variables. It's just to help us see. Let call this y. Let y be x minus mu. If y is x minus mu, what happens? The bounds don't really change, stays the same. Instead of calling x minus mu, I'm gonna call it y. So this would be e to the negative y squared over 2 sigma squared dy. This is 1 over the square root of 2 pi sigma, right? That's all I did. All I did was I rewrote it. And then if you notice, I can take out the mu. I'm going to take out the mu. But you know what I'm going to do? I'm going to put back the 1 over square root of 2 pi sigma times e to the negative x minus mu squared over 2 sigma squared dx. But what is this? What is this beautiful 1? Right, this is what we just showed. We just showed that the PDF, this is indeed is the PDF of my, this is the PDF of my random variable, normal random variable. This is f of x. I just showed this equals 1. So what's left here? Mu. And then what is this? Does anybody know what this integral is? You don't have to evaluate anything. You don't have to do any special, you don't have to do anything special. No integration techniques. And it is not 2 pi, sadly. Radical 2 pi. So you're expecting this to be radical 2 pi, right? So things cancel out. Actually, no. This actually equals 0. And I know this is 0 without having to do anything. Why is this 0? Because the integrand itself is an odd function. This is an odd function. What is an odd function? F of negative x equals negative f of x. This definitely came up in Calc 2 somewhere, somehow. The idea of odd functions or even functions on a symmetric bound, integration bound. So we're integrating an odd function. Why is it odd? Because look at this, y squared, right? Our variable here is squared. So this here will always be, this is an even function, actually. This is even. But this y, the moment we tag along this y now, when you check whether this is an odd function, you would get this algebraic property. It would hold for this. So you're integrating an odd function on a symmetric integration, bounds of integration. So odd functions, remember, if you note, they're functions that are symmetric across the origin. So the idea is that when you take the area in a symmetric bound, right? If this is a and this is a of a odd function, then the areas here will cancel each other out. And that's the idea of what happens here. And so therefore it's 0. So 0 times anything, 0. So this whole thing is 0 plus mu. And then what did I just show? I showed that the expected value of a normal random variable is simply mu. That's all I did. Which was already expected because mu was considered to be the mean. I said that in the beginning without actually proving it or showing it. And now I've shown it. I've shown that mu is the, this little Greek letter mu in the way the PDF is described, right? The the PDF of my random variable is described. This mu indicates the mean or the expected value of my normal distribution. And then we also have the variance. So the variance should be it's a similar idea. So the variance of my random variable, remember, is the expected value of x minus mu squared. So that's what it is, right? So then what should help is writing this as using the formula negative infinity to infinity of 1 over the square root of 2 pi sigma. This is going to be multiplied by x minus mu squared multiplied by, let me just rewrite this. This here is the integral from negative infinity to infinity of x minus mu squared f of x dx. That's by definition. And what is f of x for the random variable? It's that whole monstrosity that you would see, right? So 1 over the square root of 2 pi sigma. This will have the x minus mu squared. And this will be e to the negative x minus sigma squared over 2 sigma squared, x minus mu squared over 2 sigma squared dx. So that's the formula. And now the thing is, what do we do here? So what we're going to do here is something similar as we've done in the previous derivation, which is I'm going to let y equal x minus mu over sigma. Okay, so when I do that, the bounds of integration stay the same. I'm going to have y squared pop out here, but this is x minus. So I'm going to rewrite this as x minus mu is equal to sigma y squared. Sigma, right? Sigma y. So when I replace x minus mu here with sigma y, I get sigma y squared. So the y squared appears and also the sigma squared appears, but sigma is a constant, so I can put that outside of the integral, and then I'm left with e to the negative, and the same thing happens, right? I get sigma, I'm gonna write this in pink, so I get sigma squared y squared all over 2 sigma squared. And then what is dx? Well, from here, what is dy? dy is equal to 1 over sigma dx. So sigma dy is equal to dx. So then I'm left with a dy here. And then I'm also left with another sigma here. But this little constant sigma here is canceled out with the sigma in the denominator. So I'm left with this here. So the final thing I have is sigma squared over the square root of 2 pi from negative infinity to infinity of y squared e to the sigmas here cancel out. And I'm left with e to the negative y squared over 2 dy. So this is what I have. Okay. So then at this point, so a lot of this stuff, guys, it's like reviewing integration. Like I said, integration now is going to be a huge thing. It's going to be a huge thing. So an essential part of this derivations and evaluating probabilities. So I'm going to write this as y multiplied by y e to the negative y squared over 2 dy. I'm going to use integration by parts. integration by parts. So I'm going to say u is equal to y, and I'm going to say v prime is equal to y e to negative y squared over 2. And then I do this thing, right? I do u is du or u prime is equal to y prime, which is just dy, right? And then I'm just gonna write it like this: du is dy, and then v. What is v? V is equal to it's equal to, so the antiderivative of this was what? Is e to the negative y squared over 2, and it's a negative, right? And by integration by parts, what is this going to be? So this is u sigma squared over the square root of 2 pi. And then I'm going to have y, negative y e to the negative y squared over 2. And of course, I'm just going to put this all together here, right? So this whole thing is equal to, when you do integration by parts, is u times v. And then the next thing is going to be plus the integral of dv, right? It's usually the way I do it is uv, and then this is duv. So what's du? It's just dy, and this will be negative e to the negative y squared over 2 dy.
Professor, shouldn't it be negative 2e?
Say that again.
Shouldn't it be negative 2e?
Negative. You're talking about this one here?
Yeah.
Negative 2e. Well, remember when you do chain rule, you take the derivative of this. When you take the derivative of this, you have to do chain rule. What's the derivative of negative y squared over 2?
Oh, yeah. Sorry.
No, it's okay. Yeah, the twos here cancel when you distribute, right? So then this is the antiderivative of this. So you guys remember? So this should be there should be a minus here, right? Minus negative, and this is negative infinity to infinity. Again, the integration by parts formula is really just, it comes from the product rule. So you can find the formula for integration by parts using the product rule. So then what happens here? What happens here? Oh, and this is also defined from, negative infinity to infinity. Okay. So this becomes, this negative times negative is a positive. So this is positive, negative infinity to infinity of e to the negative y squared over 2 dy. And then this is this here is negative infinity and then goes all the way to negative infinity. Well, let me just see what happens. What happens when I do this? Well, this is the same thing as the limit as y goes to infinity of negative y e to the negative y squared over 2. And I'm subtracting this from the limit as y goes to negative infinity of negative y e to the negative y squared over 2. So this is one of those things, right? So what is the limit as y goes to infinity of negative y e to the negative y squared over 2? You can write this as the limit as y goes to infinity of negative y and put this over, this is e to the y squared over 2. So when y goes to infinity, this goes to infinity. When y goes to infinity, this goes to negative infinity. This is one of those uh, instances where you can apply L'Hopital's rule, right? Or you can say, well, this is an exponential function. This is a linear function, and you're going to infinity. Obviously, an exponential function will grow much larger than a linear function. So this is growing much big at a much faster rate as y goes to infinity. So when you get something that's smaller above than when something is smaller in the numerator than in the denominator, at infinity, this is approaching the value of 0. So this entire thing here, is just approaching 0. So this entire thing goes away. This entire thing here just becomes 0. So then this entire thing, again, is still being multiplied by sigma squared over the square root of 2 pi. So we just, again, this is just some scratch work for this here. And then here we have sigma squared over the square root of 2 pi multiplied by the integral from negative infinity to infinity of e to the negative y squared over 2 dy. But what is this? We showed this to equal what? All the way back here. So remember, we started with saying I is equal to this, and then we realized I was what? I was square root of 2. So this is exactly the square root of 2 pi. So this integral comes up again. It came up again right here. So this will equal sigma squared over square root of 2 pi multiplied by the square root of 2 pi. And guess what happens? I get sigma squared being the variance of x. Which is consistent, because then when we talk about standard deviation, what's the standard deviation? Standard deviation is the square root of the variance of x. But if the variance of x is sigma squared, then the standard deviation is indeed sigma. So everything works out, guys. Yeah, this was a lot of derivation for this random variable. But again, once we get over this, we're not gonna do these kind of derivations again. So what have we learned? We have learned that the PDF that we were given for the random variable with those constants, the square root of 2 pi, and all of those other constants such as e, this entire thing here is a PDF in itself. We found that the expected value of my random variable, normal random variable, is the constant mu, and that is going to be considered my mean. And my variance is the constant sigma squared. Okay. Okay, so this works for every, this is true for every normal random variable. The variance will always be sigma squared, whatever that is, and the mean will always be mu, whatever that is. Now, there's one particular kind of normal random variable that is essential to do any problem, to solve any problem related to normal random variables, and that's the standard. That's the standard normal random variable. The standard normal random variable is a normal random variable when something specific happens. This is when the mean, the expected value, is equal to 0. And when the variance, which is sigma squared, is 1, which indicates that the standard deviation of x, sigma is 1. Very important, guys. Very, very important. Okay, so then just to give you another visualization of this, it's the same bell curve. The bell curve in itself doesn't, the shape of it doesn't change. What does change are the mean and the standard deviation. So the normal distribution, standard normal, is when the middle is 0. That's the mean. And you separate everything by 1, 2, and 3. This is -1, -2, -3. This is the standard normal. And what we're going to do is, and given any random variable, normal random variable, we'll always find a way to, I guess, shrink it or to manipulate it so that it falls into this kind of standard normal. Because we have a lot of information about this particular normal distribution. And we're going to use with the cumulative distribution function, cumulative distribution. So normally we have this symbol here, this symbol, something like this, to indicate the normal distribution, which is, again, the normal distribution, the CDF is defined as everything up until x of my PDF, right? So that's when you have an x value somewhere, and you're accumulating all of the area underneath up until x. That's what this is. This is f of x, right? Now this is when f of x is when what happens when mu is 0 and sigma is 1. So when that happens, look at the function that we have. We get 1 over the square root of 2 pi, -infinity to x of e to the, call it a different variable, y squared over 2 dy. Yes, very good question. So what is the scale of the sigma? I mean, what does the x-axis scale indicate? So go back to every single other graph that we use to explain a PDF or a PMF of a random variable. The horizontal axis represents the values of the random variable. So the random variable we have here is a normal random variable. And remember, a normal random variable is under the umbrella of continuous random variables. And continuous random variables, the values of the continuous random variable is everywhere between -infinity to infinity. Hence the term continuous, because this is a continuous stream of numbers between -infinity to infinity. It's unlike discrete, right? Discrete has specific. It's 1, 2, 3, 4, and then it kind of just sticks with those discrete values. But now with the continuous random variables, we're dealing with a continuous stream interval of numbers. So the random variable goes from -infinity to infinity. And everything in between can be a value of x. But because this is a very special random variable, we have most of our values of x are between these numbers, -3 and 3. Okay. Yeah. So again, this is just a very particular structure behind. There's a particular structure behind this random variable. It's very, very nice. It's very symmetric, and it's very useful. not all random variables, as you have seen, have this very beautiful structure. Like the one with the uniform random variable is very simplistic, I would say. It's just a constant function over a particular interval. That's the PDF. So there's not much to say. But now with this, there's a lot more to say. And then why y squared and not just 1? Well, remember the PDF. Don't forget what the PDF of a normal random variable is. It's this entire thing, right? So
Right.
this is
So
the, yeah.
x minus mu is just 1 minus 0. So
No,
it's
no,
just,
no, 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 no. X is not 1 minus 0.
oh,
Mu,
x is not right.
mu is 0. Sigma is 1. So when sigma is 1, that goes away, right? It just becomes 2. This goes away. And then when mu is 0, x minus 0 is just x. So that's why there's just that's why it's just the variable squared. And remember the variable, this variable is the value of the random variable that we're dealing with. And that's why I'm going from negative infinity. Well, it's going from negative infinity to, in this particular case, it's x, but negative infinity to infinity. The values of my random variable could be anything between negative infinity to infinity. Right now, we're talking about the cumulative distribution function for the random variable, normal random variable, which is just accumulating the area underneath this PDF, which is exactly what f of x is. It's the PDF. And I'm finding the area underneath from negative infinity all the way to x. And this here, this, don't worry so much about the integral now. It's just that this is what's important. This here represents the area underneath the curve from negative infinity to x. It's underneath this curve. That's what the PDF, that's what the CDF represents. It's this area. Okay. And so the idea is we're going to be using a table, and I think your textbook definitely has it. You can, if you don't have a textbook at the moment, you can Google. This is the table that that we'll be utilizing to find the area underneath the curve, which would give us the probability. So if you notice, for example, how do we use this? For those of you who haven't seen this, x is the random variable, right? And we have a column here, and we have a row here of numbers. So if we look at x at 0 0.00, this just means it's just 0, right? X is 0. So x here, we're talking about this here. What does this mean again? This is the area under the standard curve to the left. To the left, to the left. So we're doing everything to the left. Obviously, right? The area underneath here is what? Is half the area of the entire curve, correct? Because we're going right smack dab to the middle. Remember what we just proved, though. We proved that this entire area would be what? The entire area underneath this curve would be 1. So then half of this would be what? 0.5 or a half, which is exactly what this is saying. That's what this number is saying. Now, let's suppose we go to x being 1 at 1, at 100. What does that mean? What am I calculating? I'm calculating the fact I'm doing this. I'm calculating this entire area here. So this region here is what? This is the cumulative distribution function when it's less than or equal to 1. So this is like saying, what's the probability that my my random variable is less than 1? That's what I'm saying. And then how do I compute that? I compute that by looking at this table. So this is 1, 0, and this area here is what? 0.8413. Could you say it's 1 standard deviation from 0? Yeah. Well, what I'm saying is this number here, 0.8413, is the probability that my random variable is less than 1. That's all I'm saying. Which is 1 standard deviation above the mean. Above the mean. Okay, so the probability that my random variable is less than 1 standard deviation above the mean would be 0.8413, which would be approximately 84% of the time. So 84% of the time, the random variable would be less than 1 standard deviation above the mean. So you also have to worry about 1 standard deviation being below the mean, which would be at -1, and so on. Okay, so that's how we're going to be utilizing this table. It's the area to the left. And then the question will be, how do you find the area to the right? Let's say I want to find the area to the right of this. Then I would have to do what? I would have to do 1 minus, exactly. I'd have to do 1 minus the area to the left. So that's the idea behind utilizing this table and interpreting what these numbers here mean. They're just the area to the left of the value of x. And let me just say one last thing, and then we'll just end. The standard normal distribution we normally denote using z. Whenever you see z, so I'm going to replace all of this, okay? So I'm going to replace this with z. Normally z is so I think I can, yeah, I'll just leave it like that. But normally z is what's utilized to denote standard normal. So whenever you see z, uppercase, think standard. X is just a general random variable, but z particularly is the standard normal distribution. Okay. All right, guys, so our time is up. I will stop my recording here.